Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Sahib Noor and welcome to a new lecture of Physics 2. This is our lecture number 7 of the course, and we will study topics from chapter number 18. The title name of the chapter is Heat, Temperature and First Law of Thermodynamics. The topic of this lecture will be to study the temperature, which is one of the fundamental physical quantities, and then we will study the Zeroth Law of Thermodynamics, in which we compare the temperature of few bodies in the transitive method, and then we will discuss the different scale of temperature and measurement the temperature at and will measure the temperature at different scales. And then the effect of the temperature is known as a thermal expansion, in which the size of the object will decrease by increasing or decreasing the temperature. And our last topic will be to discuss the heat, the energy which flow due to the temperature difference from one body to other body. So let's start our first topic of the lecture, which is temperature, and we will introduce the temperature in this slide. Temperature is one of the 7 SI based quantities. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Although the temperature of the body apparently has no upper limit, it does have a lower limit. This limiting low temperature is taken as 0 of the Kelvin temperature scale. Room temperature at the Kelvin scale is taken as 295 Kelvin, while the temperature of the universe in the beginning is 10 power 39 Kelvin, which is a very high temperature. And a chart has been shown at the right hand side of the slide, in which the temperature is drawn vertically, and you will see that the most highest temperature at the beginning of the universe is recorded as 10 power 39, and the lowest recorded temperature in the laboratory is 10 raised to the power minus 9 Kelvin. And some other temperature with which you are familiar, the water freezes at 10 power 2 Kelvin, or the temperature of the surface of the sun is recorded as in between 10 power 3 and 10 power 4 Kelvin, while the highest temperature which is recorded in the laboratory is 10 power 8 Kelvin. And the average temperature of the universe is now 3 Kelvin, and this is like as 10 power in between 10 power 0 and 10 power 1. And as the universe expand, it cooled, and now the average temperature of the universe is 3 Kelvin. We on the earth are a little warmer than that because we happen to live near a star. Now in this slide we will discuss the introduction of thermodynamics and the Zeroth Law of thermodynamics. One of the principal branches of physics and engineering is the thermodynamics, which is the study and application of thermal energy, often called the internal energy of the system. And what is thermal contact and thermal equilibrium? So if two bodies exchange energy due to temperature difference are in thermal contact with one another, and if the energy transformation in thermal contact stops, then the body are in thermal equilibrium. So when the body touch one another, and if there is a temperature difference, then we can say that the bodies are in thermal contact, and the energy transformation will stop when the temperature of the bodies are equal to one another. And then we can define the zeroth law is, if the bodies like A and B are each in thermal equilibrium with a third body T. So if body A and body B are in thermal equilibrium with a third body which is taken as T, then A and B are in thermal equilibrium with each other. So here we make a relation of A and B with a third body, and if A is in thermal equilibrium with body T and B is also in thermal equilibrium with a body T, then the temperature of A and B will be equal. And we can summarize this law as, when the two bodies are in thermal equilibrium, their temperatures are equal and vice versa. In this slide we will discuss three different scales of temperature, which are Kelvin, Celsius and Fahrenheit scales. To develop temperature conversion relation, we can select the freezing points or boiling point of water. For technical reason, we can also select the triple point of water, which is liquid water, solid ice and water vapor, that is gaseous water, can coexist in thermal equilibrium, and that point is known as triple point of the water. And here you are seeing that we have three different scales: Fahrenheit, Celsius and Kelvin. And water freezes at 32 degree Fahrenheit. At the Celsius scale, the temperature of the freezing water is 0 degree centigrade, while at the Kelvin scale it is 273. When the water boils at the Fahrenheit scale, it boils at 12 degree Fahrenheit, and on the Celsius scale its temperature is 100 degree centigrade, while at the Kelvin scale it is 373 Kelvin. And we can make a relation between Kelvin and Celsius scale is, we take temperature at Kelvin scale and minus the freezing point of the water at Kelvin scale is 273, and the difference between the boiling point and the freezing point of water at the Kelvin scale is 100. So we divided this by 100, and similarly we take the temperature at the centigrade scale and subtract the number which is represent the freezing point of water at the Celsius scale, which is 0, and divided it by the difference between the freezing point and boiling point of water at the Celsius scale, which is 100. And we can derive Tc, which represent the temperature at the Celsius scale, is equal to Tk minus 273, or Tk is equal to Tc plus 273. Similarly, we can develop a relation between Kelvin and Fahrenheit scales, like Tk minus 273 divided by 100, which is equal to Tf minus 32, which represent the freezing point of water at the Fahrenheit scale, and the difference between the boiling point and freezing point of water is 180 degrees. And we can derive Tk is equal to 5 or 9 into Tf minus 32 plus 273, which means that if we know the temperature of a body at the Fahrenheit scale, we can convert it into the Kelvin scale's temperature. Similarly, we can also derive a relation between Fahrenheit and Celsius scale, and remember that the Celsius scale is also known as the centigrade scale, and we can write Tc minus 0 divided by 100, which is equal to Tf minus 32 divided by 180 degree, and we can derive the relation for Tc or Tf as Tc is equal to 5 by 9 into Tf minus 32, and if we know the temperature at the Fahrenheit scale, we can convert easily it into the centigrade scales. Our next topic of the lecture is the thermal expansion, and in this slide and the upcoming slide we will discuss two types of expansion, which are linear and volume expansion. The properties of many bodies change as we alter their temperature, perhaps by moving them from a cold to a hot place. As their temperature increases, the volume of the liquid increases, a metal rod grows a little longer, and the electrical resistance of the wire increases, and all the objects change size with changes in temperature, and such a expansion in the size or such a expansion in the dimension of the object is due to the thermal expansion. Such a thermal expansion of the material with increase in temperature must be anticipated in many common situations. For example, when a bridge is subjected to a large seasonal changes in temperature, the section of the bridge are separated by expansion slot, so that the section have room to expand on hot days without the bridge buckling. And when there is the increasement in the length of the object due to increase in the temperature is known as the linear expansion. In the adjacent figure, two metals are taken of same length at the room temperature, so their length are taken to be the same, but when the temperature increases, one of the length or both length can increase, and the increasement must not be the same as we have two different material. So when the temperature increase and there is an increasement in the length of the object, such an expansion is known as a linear expansion. And if the temperature of the metal rod of length L is increased by amount delta T, then the length is increased by amount delta L, which is equal to alpha time original length into change in the temperature, where alpha is known as the coefficient of linear expansion, and the SI unit of alpha is per degree Celsius or per Kelvin, and the properties of alpha depend upon the properties of the material. In this slide we will discuss the volume expansion. If all dimension of a solid expand with temperature, the volume of that solid must also expand, and the volume expansion for liquids is the only meaningful expansion parameter. So if the temperature of the solid or a liquid whose volume is V increased by amount delta T, then the volume is increased by amount delta V, which is equal to beta times initial volume multiply change in the temperature, where beta is known as the volume expansion. The coefficient has the unit per degree Celsius or per Kelvin, and it depends upon the material of the object. So beta is known as the volumetric coefficient of expansion, and the SI unit of beta is per Celsius or per Kelvin. And for solid, the relation between the coefficient of volume expansion and the coefficient of linear thermal expansion is given as beta is equal to 3 times the coefficient of linear expansion, which is alpha. So beta is equal to 3 alpha. In this slide we will present an example to understand the volume expansion. The statement of the problem is: on a hot day in Las Vegas, an oil trucker loaded 37,000 liters of diesel fuel. He encountered cold weather on the way to Payson, Utah, where the temperature is 23 Kelvin lower than in Las Vegas, and where he delivered his entire load. How many liters did he deliver? The coefficient of volume and linear expansion of the steel truck tank is given as this one and this. So we have to calculate it first, the change in volume, and then we'll find that what is the final volume of the diesel fuel. So to find the change in volume of the fuel, we will use formula delta V is equal to beta V delta T, where beta is the coefficient of the volume expansion, V is the initial volume of the fuel, and delta T is the change in the temperature of the two cities. So we will put these numerical value and our answer is minus 808 liter. So the change in volume is 808 liter, and the negative sign show that the temperature of the Payson, Utah is lower than the temperature in the Las Vegas. So we put the negative sign for that reason. So we can find the final volume or the volume of the fuel which is delivered in the Utah, which is equal to V plus delta V. V is the initial volume plus delta V is the change in the volume which is encountered in the traveling. So 37,000 liter is the initial volume and the change in the volume is 808, and we put the negative sign because the volume is reduced and the delivered volume of the fuel is 36,190 liter. Now the question is, who paid for the missing diesel fuel? Now our next topic of the lecture is heat and internal energy, which is also called the thermal energy of the system. But before discuss heat and internal energy, we will discuss about the terms which is system and its environment. So anything which is under observation, like a cold cola or a hot tea cup placed in space, is called a system, and the relevant parts of the space other than system is called environment, and the temperature of the environment is taken as TE, while the temperature of the system is represented by TS. Our observation is that if the temperature of the system is not equal to the temperature of the environment, then the temperature of the system will change until the two temperatures are equal, and thus thermal equilibrium is reached. So the transferred energy between system and its environment is due to the temperature difference, which is known as heat. The symbol for heat is taken as Q. The thermal energy is often called the internal energy, which are consist of kinetic and potential energy associated with the motion of the atoms, molecules, and other microscopic object of the system. Now after discussing the system and environment along with the heat is energy due to temperature difference, so it is a binary process. Heat can be transferred into the system or transfer from the system to environment. So we will represent heat as a positive and negative energy. Heat is positive when the energy is transferred to a system's thermal energy from its environment. That is, when heat is added from environment to the system, then that heat will be positive. And heat is negative when energy is transferred from a system's thermal energy to its environment. So when the energy is transferred from system to environment, so the thermal energy of the system will reduced, and we will represent that transferred heat as a negative energy. And there are some units of heat. Calorie is one of them, which is defined as the amount of heat that would raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. That is, when 1 gram sample of water is taken, and when we raise the temperature of that sample from 14.5 degrees centigrade to 15.5 degrees centigrade, that is, the temperature difference is 1 degree centigrade, then that amount of heat which is transferred is known as 1 calorie. There are another unit which is BTU, British Thermal Unit, and defined as the amount of heat that would raise the temperature of 1 pound of water from 63 degree Fahrenheit to 64 degree Fahrenheit. Again, we have a temperature difference of 1 now, and this time we have a Fahrenheit scale, and the amount of water is 1 pound. And the SI unit of heat, as heat is energy, and the SI unit of energy is joule, and these three units can be related with one another by this expression. 1 calorie is equal to 3.968 multiplied 10 raised to power minus 3 BTU is equal to 4.1868 joule. So calorie is a bigger unit than joule. 4.1868 joule makes 1 calorie. Now in this slide we will present some figure which will show us that heat can be taken or added to the system. So in first figure we have a system and its environment. TE represent the temperature of the environment, while TS represent the temperature of the system. And when TS is greater than TE, that is, the temperature of the system is greater than the temperature of the environment, then heat must be transferred from system to environment. And the outward arrow show us that the heat is transferred from system to environment, so Q is negative, which is less than 0. And if the temperature of the environment and the temperature of the system are in equilibrium, so we can say that the system is in thermal equilibrium with its environment. So Q is equal to 0, which show us that heat nor enter to the system nor leave the system. And in third figure, when the temperature TE is greater than TS, then heat must be added to the system. So this inward arrow represent that now Q, heat is added to the system, so Q is taken as a positive, so Q is greater than 0. So let's sum up our lecture number 7. What we have studied in this lecture, we have discussed temperature, which is one of the base SI unit, and we have discussed 3 different scale related to temperature, that is the Fahrenheit scale, the centigrade scale, and the Kelvin scale. And then we have discussed the effect of temperature when the temperature raises the size of the object or change, and we have discussed the linear and the volume expansion of the object. At final stage of the lecture, we have discussed heat, which is energy transferred due to temperature difference, along with the internal energy, which is related with the kinetic energy and potential energy of the molecule or atom of the object. In next lecture we will discuss about the work done by the system or work done on the system along with the first law of thermodynamics. We will also discuss the application of first law of thermodynamics. And if you have any question or any difficulties related to this lecture, you can contact me at my email. Thanks and Allah Hafiz.